In this video, we are discussing matter and some of its properties. So this is an introduction to the topic molecules, compounds, and chemical equations. So what I'm going to do in this video is to introduce you to important concepts, but then we will do a lot more, especially the math part of it, during our class session. So just make sure that you watch the video and you answer the questions pertaining to this video. Then be prepared to solve problems in the classroom. Molecules, compounds, and chemical equations. So the objectives of this lesson is for us to be able to define and classify matter, and also to discuss ionic and covalent compounds. So I'll just introduce these types of compounds. First, what is matter? Matter is anything that has mass and occupies space. Occupies space means it has volume. So matter is anything that has both mass and volume. In terms of classification, we can classify matter as pure substances and mixtures. So these are two broad classes of matter. A pure substance is made up of one element or one compound. So when we talk about a pure substance, we think of an element or a compound. But that should be present as a single element or a single compound. Examples of pure substances are gold, pure carbon dioxide, distilled water, silver, pure oxygen. A mixture is made of more than one element, one compound or both. So in a mixture, we can have two elements. We can have an element and a compound. We can have two compounds or more than two compounds. Examples of mixtures are milk, air, salt solution, sand, and rocks. So we can see milk is a mixture that contains water, sugar, fat, protein, among others. While air is a mixture that contains nitrogen molecule, oxygen molecule, argon, carbon dioxide, water vapor, among others. So this is the general classification of matter. We start with our broad picture, matter as the title holder for everything that has mass and volume. So we ask questions. Like one of the questions is, if it is matter, does it have only one substance? If the answer is yes, then you know that part of matter is a pure substance. If the answer is no, then you know that part of matter is a mixture. So we go back here. We say, all right, it's a pure substance. We ask another question. Does it contain some kind? Does it contain the same kind of atoms or the same type of atoms? If the answer is yes, if it is made up of the same type of atoms, if the answer is yes, that is an element. If the answer is no, that is a compound. On the mixture side, if you ask, is it uniform? If the answer is yes, it is a homogeneous mixture. If the answer is no, it is a heterogeneous mixture. So we'll define these homogeneous mixtures and heterogeneous mixtures in due course. Now, let's look at just pure pure substances, that is elements and compounds. How do we classify the pure substances? So pure substances can be classified as elements or compounds. So you can use similar type of questioning like we did the previous slide. Elements themselves can also be grouped into two parts. We have atomic elements and molecular elements. So an example of atomic elements is neon. Neon is found as a single atom in nature. An example of molecular element is oxygen. So oxygen in nature exists as a diatomic molecule. That is on the element side. On the compound side, we can also have two groups from there. So we have a molecular compound when the compound is made of non-metals only. Then we have ionic compounds when the compound is made of a metal and a non-metal. So an example of a molecular compound is carbon dioxide. A compound contains two or more elements that are chemically bonded. So we can see in this case we have carbon as an element and we have oxygen as an element, but when we combine them we form a compound carbon dioxide. In terms of ionic, we see that sodium here, Na, is a metal. The chlorine here is a non-metal. So having a metal combining with a non-metal, we get an ionic compound. So we can represent pure substances using diagrams. And these diagrams are very important. Please study them carefully. You need to understand them. In the exams, I want you to be able to draw these diagrams for me. So elements. You can show an element like atomic element just as single atoms. This is atomic elements. A molecular element can be shown by having multiple atoms making a single element. So in this case, we have this atom combining with this atom to make a single element. So we can say a single element here, single element. But a single element made of two atoms. Some elements can have as many as 8 atoms, like sulfur H, S8. In terms of compounds, we have ionic compounds. Ionic compounds are three-dimensional structure, solid structure made of alternating a metal and a non-metal. So in this case here, we have a metal here, non-metal here. Metal, non-metal, metal, non-metal, metal, non-metal, metal, non-metal. So it's alternating metal and a non-metal to form this three-dimensional structure that we will see in later slides. While molecular compounds, most of the molecular compounds, they are made of just single molecules. They are not connected like what we see in the ionic compounds. They are made of single molecules. That's why most molecular compounds have low boiling point or low melting point because they do not have a structure like in the case of ionic compounds. So here we can see this is kind of a water molecule. So the water molecule will exist as a single molecule, single molecule, while an ionic compound does not exist as a single molecule. Here we can say this is a single unit, but the single unit does not exist on its own. While in molecular compounds, single units exist on their own. And because of that, molecular compounds mostly have low boiling and melting points. But the question is, do we have a situation where molecular compounds can exist also as three-dimensional structures? The answer to that question is yes. We have that situation, especially when we deal with carbon, as we will see later. Now, what about mixtures? What are the types of mixtures? In terms of mixtures, we have two types of mixtures. The first one is homogeneous mixture. In this case, substances are distributed uniformly such that you cannot identify individual components of the mixture. The mixture has a single phase. That is, if someone asks you, all right, this is a mixture, a sugar solution, can you identify where the sugar is? Can you identify where the water is? In that type of mixture, you are not able to do that. So we have an orange juice here. Orange juice is made of the orange juice and some water in it. So the question is, can you make out where the actual orange juice is or where the water is? No, because it is a homogeneous mixture. Some examples of some homogeneous mixture, as I already said, we have salt solution, air, sugar solution, soapy water, steel, brass, and bronze. So we know air is made of these nitrogen, oxygen, but it's difficult to say, oh, where is oxygen in air? Where is nitrogen in air? Then we have heterogeneous mixtures. Heterogeneous mixtures consist of two or more substances that are not uniformly distributed, such that you can identify individual components in a mixture. So this is an example. Yeah. So here you can collect different MMMs and be able to separate them easily. That's the easiest thing about heterogeneous mixtures. Some of the examples: sand and salt mixture, iron filings and salt, soda, chicken noodle soup, and the like. So the another major difference between homogeneous and heterogeneous mixtures is that it's easy to separate heterogeneous mixtures because you can just collect the things by hand. Here I can just collect these ones by hand. But it's very difficult to separate this mixture. I need to use all means available to me to be able to separate water from the orange juice. We can also represent mixtures and pure substances using diagrams. Please study the diagrams, understand them. They are extremely important. So the first diagrams, I'm showing elements. We have two types of elements here. We have atomic elements, single atom, and then we have molecular elements. So these are pure elements. The second part is the pure compounds. So this looks like water. So you need to be able to draw a diagram. If I ask you, can you draw me a diagram of elements? Can you draw me a diagram of an atomic element or a molecular element. Can you draw me a diagram of a pure compound? So this is an example. So the difference is that a pure compound has different atoms. As you can see here, we have one type of atom here and then another type of atom. Then here we have mixtures of elements. So you can see this element is mixing with this element in this case. This element is mixing with this element. This element is mixing with this element. So these first three are mixtures of elements. This one is a mixture of an element and a compound. So this is a compound and this is an element. So if I ask you, can you draw me a diagram showing a mixture of an element and a compound? This is the example. Or during an exam, I can give you a multiple choice question with these diagrams and say, all right, identify mixture of elements. Identify mixture of elements and compounds. You should be able to do that. Now I move on to changes in nature. So we have two types of changes in nature that happen in nature. We have a physical change and a chemical change. In a physical change, it is a change that only affects the form of a substance, but does not affect the substance's chemical composition. In other words, no new substance is formed. For example, if you are melting water, right? So you have ice and you want to melt it into liquid. Yeah, you are just melting it from ice form to liquid form, but it is still water. The chemical composition is still water, whether in ice form or in liquid form. It is the same if you are boiling water from liquid water to water vapor. The composition is still the same. It just changes from liquid to gas. So that is a physical change. Another physical change is mixing salt and pepper. I think I wanted to say the pepper, the spice, not the pepper like we used to write on. So you can check the spelling. This is also a physical change. If you are cutting down a tree, that is a physical change. Now we have a chemical change. In a chemical change, there is breaking and formation of chemical bonds. And because there is this breaking and formation of a chemical bonds, a new substance is formed. So when you see that there is a new substance formed, you know this is a chemical change. Examples are rust formation, that is corrosion, right? Making an omelette, burning things like campfire, you're roasting marshmallow. So those are chemical changes. One major difference between a physical change and chemical change is that it is very difficult to reverse chemical changes. You can easily reverse physical changes. For example, if you melt water, right, you melt it and it becomes liquid, you can decide, no, I don't want melted water. Let me freeze it. So you can reverse back to the solid form of water. So that is a physical change. But in terms of chemical change, if you change hydrogen and oxygen to water, it is really hard to get water back into hydrogen and oxygen. And another thing is that hydrogen is a gas, oxygen is also a gas, but water is a liquid at room temperature. So you can see that there are different properties. The reactants have their own, or the components before have their own properties. After a reaction, we have a new set of properties for that because we have formed a new substance. Now let us delve into the chemical bonds. So we have two types of chemical bonds that we are going to discuss in this introduction. The first one is ionic bond. This is formed when a metal interacts with a nonmetal. Let us take note of that. An ionic bond, you need to have a metal and a nonmetal. So look at the periodic table. Be able to determine which side of the periodic table has metals, which side of the periodic table has nonmetals. If you have sodium, magnesium, potassium, calcium, aluminum, all those are metals. If you have carbon, you have oxygen, you have fluorine, bromine, and the like, those are nonmetals. So when you see a combination between sodium and chlorine, you know that what you have is an ionic bond. In this case, the metal loses electrons and the nonmetal will accept electrons. So the sodium will lose an electron and the chlorine will grab the electron. The metal ion is known as a cation, and the nonmetal ion is known as an anion. So this is an example of what happens. Let us say we have this sodium atom or element. It has 11 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it has 11 electrons, and this is chlorine. It has 17 electrons. This electron here on the outer shell can transfer to the chlorine. So the metal sodium will lose the electron to the chlorine. When the metal loses this electron, this shell disappears. So we remain only with the shells inside. So what does that mean? When a metal loses electrons, its atomic radius will decrease significantly. As you can see, this one is much smaller than this because we have lost a shell. What about this anion? Are we going to see a change in the radius? If this electron transfers to here, initially here we have 1, 2, 3, 4, 5, 6, 7 electrons. And the electrons repel each other. But if we add another electron here, there will be more repulsions. So there will be more repulsions of these electrons in the outer shell. So what they are going to do is they are going to minimize those repulsions. This outer shell will expand a little bit. So chlorine atom has a smaller radius than a chloride ion because of that repulsion. So now what is happening in this case? This is positively charged, this is negatively charged. So we know that unlike charges will attract each other. That attraction is known as electrostatic interaction. And that attraction is what makes the ionic bond. So by definition, an ionic bond is formed when charged ions attract one another by electrostatic forces as a result of transfer of electrons from a cation, so a transfer of electrons from here to an anion. So as I already said, the positive ion is smaller than the atom. This is smaller than this. The negative ion is larger than the atom. This is larger than this. Now, as I said earlier, the ions exist in solid phase as three-dimensional structures. So the three-dimensional structures that ions exist in solid phase are known as solid lattice. By definition, A solid lattice is a regular three-dimensional array of alternating cations and anions. Cations and anions is the positive charged and negatively charged ions. So if we slice the crystal or the solid lattice into half, we are seeing it from one face. Cl sodium, Cl sodium. And we need to take note that usually the anion is bigger than the cation. If we look at it in now the actual three-dimensional structure, this is the solid lattice of anions. This is a metal, nanometal, metal, nanometal. So we can say that each sodium here is surrounded by 1, 2, 3, 4. The other, that side has another sodium, another chlorine, and this side also has another chlorine that we cannot see now. Let's look at the covalent bond. Now, this is formed when nanometals interact with each other. So when you have a nanometal interacting with a nanometal, we have a covalent bond. In this case, bonding atoms will share electrons to form a molecular compound. The official definition: a covalent bond is a result of strong electrostatic interaction when two nanometals share electrons to form stable entities. Covalently bonded atoms form molecular compounds. So when I say covalent compound, it is the same as a molecular compound. As I said earlier, normally covalent compounds, the atoms, the molecules themselves exist as single units. But in some cases, they exist as three-dimensional structure. So one of them is diamond, as you can see here. Graphite, as we can see here. So these are the three-dimensional structures of diamond and graphite. Both of them are made of carbon. Now let's practice. What statement best summarizes the difference between molecular and ionic compound? So you would want to stop this video for now and think about the problem, read it properly, think about the answer, and then I'll give you the answer. Alright, I think it's okay now to give you the answer. Here the answer is C. Molecular compound contain covalent bond formed as a result of electrostatic interaction through sharing of electrons between atoms. Ionic compounds contain ionic bonds formed as a result of electrostatic attraction through transfer of electrons. So the difference is we have sharing of electrons for molecular compounds and transfer of electrons for ionic compounds. Identify the following compounds. This one, please study it. It's very important. For the exam, you should be able to identify the compounds. So stop this one video and think about it. Make sure that you feel all of them before I give you the answer. So the first one is covalent, the second one is ionic, the third one is ionic, this one is covalent, this one is covalent. So molecular is the same as covalent. Why is this covalent? C is a nanometal, H is a nanometal. So nanometal form covalent bond. What about this? Why is it ionic? K is a metal, SO4 is a nanometal. So metal, nanometal, ionic. This one is also ionic for the same reason. Magnesium is a metal, nitrogen is a nanometal. This one is covalent because carbon is a nanometal, sulfur is a nanometal. This one is also covalent because hydrogen is a nanometal, chlorine is also a nanometal. So let's take note of these. The secret is if you have two nanometals or if you have nanometals only, you have a covalent compound or a molecular compound. If you have a metal in them and a nonmetal, you have ionic compound. Now let's finish with chemical formulas. The definition. A chemical formula indicates the elements present in an atom and the relative number of atoms or ions of each. So it contains a symbol or symbols of each atom and a subscript indicating the relative number of atoms of each element present in that formula. So we have different types of chemical formulas. The first one is empirical formula. This one gives the smallest ratio. It gives the relative number of atoms of each element in a compound. It gives you that smallest ratio. Then we have a molecular formula, which gives you the actual number of atoms of each element in a compound. Then we have structure formula. This one uses lines to represent covalent bonds and shows how atoms in a molecule are connected together. We are not going to use much of structure formula in this class, but these two, empirical formula and molecular formula, are very important to know for this class. So this is an example. This is a molecular formula giving you the actual number of elements in each molecule. So we have 4 carbons here, 8 hydrogen. Now empirical formula will give you the smallest ratio, 1 to 2. This one we have 6 carbon, 6 hydrogen. The empirical formula will just give you C and H. So we'll look at the empirical formula later. And these are the structure formulas. Here for carbon tetrachloride, we see that the empirical formula is the same as the molecular formula. So the empirical formula here is the same as the molecular formula. So let's make sure to study this video, to listen to this video and study the questions. We are not going to repeat these things in class because we need to do a lot of the problems, difficult problems in class. These concepts, we can do them outside class. So just be ready for the next class. Thanks.